Hey guys, in this video we are going to fine-tune BERT to classify toxic comments, and to do that we are going to use the transformers library by HuggingFace, the version 4.0, which has been newly released, and we are going to use the PyTorch Lightning library to fine-tune the model, and the end result will be a model that can do something like this. So if you have this comment and call a function classify comment and pass in the raw text to it, this will basically output a set of tags that classify this comment as toxic and a threat. So let's get started. The transformers library by HuggingFace just hit version 4.0 a couple of days ago, so I thought it is a great time to have a look at it once again, and the library is better than ever, and it's easier to use it to fine-tune some of your favorite, hopefully, transformers models. As you can see, the library contains a lot of implementations, something like BERT, BERT, which is of course created by Facebook, and it's a really interesting version of BERT, or change from BERT. Of course, the original BERT model. We have some other favorite mentions like the SteelBERT, which is a very slimmed down version of BERT as well. And the cool thing about the HuggingFace library transformers is that it is very generic, and you can use it to train, let's say, BERT, and with a minimal change of your code you can use, say, Albert or Roberto or some other version of that, as long as you want the correct pre-trained tokenizer and the correct pre-trained model. So this will be the thing that we are going to do right here. We're going to just want a pre-trained BERT tokenizer and the BERT model. Then we are going to fine-tune that for detecting toxic comments, and I'm going to fine-tune the BERT model using the PyTorch Lightning library. Recently in my work I've been using PyTorch Lightning for, let's say, a couple of weeks to a month, and I think that it is a great library. It's very similar to what Keras is to TensorFlow. So we are going to have a look at it and how you can use it to fine-tune BERT right here. Alright, so let's get started. I'm going to open a fresh notebook on Google Colab, and right here I'm going to go to runtime, change the runtime type to GPU, and I'm going to run this and let the machine connect, and let's see what kind of GPU we have here. So we have a T4 with 15 gigabytes of VRAM, so this is great and it should work great for our purpose. So after that I'm going to install the transformers library, and if you go to the GitHub repo of the transformers library, you can basically see that there is a patch release which is 2 days old. So I'm going to pip install the transformers library. Transformers. And I'm going to install the specific version, which is 4.01. And after that, I'm going to do the same thing for the PyTorch Lightning library. And the latest version is 1.10. So you can see this right here. All right. So basically the same thing. And you can use the quiet flag if you don't want to get all of this output right here. But this should essentially install both libraries that we need right here. So next I'm going to just import some libraries. So I'm basically going to copy and paste all of my imports that we are going to use right here. So you can see we are doing the standard stuff, importing pandas, numpy, torch. Then I'm going to import the dataset and the data loader for the dataset creation. Then we are importing the BERT tokenizer, the BERT model, and Adam with weight decay fix optimizer that is provided by the transformers library. And we are going to use the pretty much standard linear schedule optimizer. So after that, we are basically importing the main module of PyTorch Lightning, and we are going to use the receiver operation curve for basically evaluating how each of the possible classes are getting predicted for our toxic comments. After that, I'm doing some plotting setup, and I'm going to copy and paste the seeding and the plotting colors and palettes right here. And you can see that I'm seeding the NumPy random generator and the Torch random generator, which might not be the best way to do it, but for our purposes, it's going to be great. Next, we are going to have a look at the data, and the data is provided by Kaggle, and it's called the Toxic Comment Classification Challenge. And you can see that this challenge was set up by Google, and in it you have to basically predict how likely is that a given text contains any of those tags. So whether it is toxic, severe toxic, is it a threat, insult, and others. So there are basically 6 tags that you can apply to each text or each comment. And in here we have to do basically multilabel text classification. So the data is actually quite large. It contains a lot of comments, and you can see that pretty much this challenge is long over, and there is a lot of entries right here. You can see the different notebooks, and some of those are really good, and I suggest you go over those if you are interested in similar problems. And you can see the rock area under the curve is the metric that is used to basically evaluate how good your predictions are. Of course, the mean value of each of those possible tags right here. So let's get this data downloaded in our notebook, and I'm going to do that by using a file that I've already uploaded to my Google Drive, which is available for you as well. And you can use that gdown to download the file. And the file is basically the training comments in a CSV format. So I've unzipped the comments. And next, we are going to use pandas to load the comments themselves. All right, so I'm going to have a look at the format of the data. So here we have the comment text, ID of the comment, and we have each of the 6 possible tags, and 0 means that this comment is not toxic or not any of those. And if you see a position that we have like 10, so let's do, let's say 20 examples. So you can see a quite wordy example of what a toxic comment might be. So there are a lot of examples of that, and there are a lot of examples where each comment is, you can say, clean. Next, we are going to split the available comments into a training and validation dataset, and I'm going to use the train test split function from sklearn. And I'm going to reserve around 5% of the data for validation and testing. I'm going to check the new shapes of those data frames. And you can see that we have quite a lot of examples for training and around 8K of examples for testing and validation, which is quite good, I guess. And after that, I'm going to basically show every and each possible tag or possible label that we have. So I'm going to create a constant which contains the word toxic, severe toxic, seen, threat, and these are these ones, of course. So I can just copy and paste those. There might be a better way to do this, but yeah. All right, so we have a human readable form of what the possible columns are. And then I'm going to have a look at the distribution of the possible tags or columns. So you can see that the toxic tag is used very, very often. And then we have the on second place the obscene and insult, I guess. So after that, I'm going to get a sample of the training data. And this is something that we do because training BERT is quite slow with so many examples. And you can see that we have the T4, and even though this GPU is very powerful, still training this model takes a lot of time. And you can see how much or exactly how much later on when we start the training. So I'm going to assign a sample to the training data frame, and I'm going to sample 100k examples right here, training. And then I'm going to check the new distribution of the labels, and you can see that pretty much it is a very representative sample of the original data that we had. So let's continue with a sample of a comment, and to do that I'm going to take a row, and I'm going to take a row at index 16, and you'll see why in a second. I'm going to take the comment from that, and I'm using the comment text column. If you go right here, you'll see that we have this column. So after that, I am going to get the labels for this one, and I'm going to use the label columns right here. I'm going to print the sample comment, the text for the comment, that is, and then I'm going to represent a dictionary of what we have in our labels. So buy, don't look back, come or think of coming back, totter. So this is a toxic comment, at least from the point of view of our labels, and you can hopefully agree with that. After that, I'm going to get a pre-trained tokenizer, and I'm going to use the BERT base cased model. Why? Because mostly I believe, and that's a purely intuitive or personal opinion, I think that when people are hating our internet and they write some interesting stuff, you can sometimes see that they're using all uppercases. So this might be, let's say, an feature or a signal that this what they're talking about might be offensive or toxic behavior. So I'm going to take the base version of BERT, the cased version of the base version, and then I'm going to what the BERT tokenizer from pre-trained, and I'm going to pass in the BERT model name right here. So if we do that, you see that this goes out and downloads the tokenizer. So I'm going to use the tokenizer to encode the sample comment right here. And I'm going to use the encode plus method. So this method accepts a bunch of parameters, but it is not that scary as it might look at the first glance. So the first parameter is going to be the text of the comment in a raw format. After that, we want to add the special tokens, which are the tokens that are required by BERT. We would say that we want a max length of, let's say, 512 tokens. We don't want this tokenizer to return the token type IDs because we don't need those. And we want to apply a padding according to the max length parameter. So basically each encoding will contain 512 examples or tokens. We want the attention mask. And finally, we want to return the result as tensors in a PyTorch format. So basically this is the encoding right here. And after the encoding is complete, you can see that this encoding contains only two things: the input IDs for each token, and then the attention mask that is required by the BERT model, which we are going to train later on. So let's check the shapes of the input IDs and the attention mask that we have right now. And as expected, this is the same number that we passed in as the max length for the tokenized example. So this is something that we are going to input into the BERT model that we are going to fine tune later on. And if you are curious about what the input IDs actually contain, here are the IDs of the first 20 tokens. And we can basically do the same thing for the attention mask. And this should contain only once because, yeah, the text contains a lot of tokens, and the first, at least at first 20 examples are not missing or are actual words or tokens. So, okay, so one interesting thing that you can do right now is to convert the input IDs to actual tokens, which BERT is using under the hood. So I'm going to call the tokenizer.convert IDs to tokens, and I'm going to pass in the input IDs. And if you do that, you're going to get this error. Only one element tensor can be converted to Python scholars. So to fix this, I'm going to look at the shape of the input IDs, which includes this dimension right here. And if I squeeze this dimension, we are going to get rid of it. And if we pass in this instead right here, you get a list of tokens with a lot of paths. But I'm going to take just the first 20 examples right here. So to get this a bit prettier, I guess, you can just use the print, and you can see that we are getting some very interesting results. The don't is split into 3 tokens, and the coming word is split into come, and then something that is probably very, very often found in text. Again, for the tosser, we have this right here. Again, something very interesting. And of course, those are learned from the pre-training of the BERT model. Okay, so let's continue with creating a dataset which represents toxic comments. And in this dataset, we are going to basically extend the dataset class that is provided by the standard PyTorch library. And I'm going to call this class toxic comments dataset. And in here, we are going to define a constructor which accepts a data from a data frame, and I'm going to type him this. It's gonna accept a tokenizer, which is going to be the BERT tokenizer. And we are going to accept another parameter, which is going to tell us how much, what the length of the tokens is going to be. And this is going to be an integer with a default value of 128. So let's assign a fields for each of those examples. And we basically have to override two methods in here. The first is going to be the method len, which tells the size of the dataset. And we are going to return the length of the data frame. The next method is the getItem method. And this one accepts an index of the item that we want to return right here. So from this, I'm going to take the data row from the data frame that we have as a data. And I'm going to use the iWalk method from pandas. Now that we have a single row, and once again, a single row represents something like this. So this is a single row, it contains the comment text and each of the tags that we have here, as well as the ID of the comment, which we are not using. So I'm going to take the text. Then I'm going to take the labels, which are basically all of the columns that contain the tags for the comment. And we have those stored into label columns. And it appears that my runtime has disconnected. And I don't currently have a GPU, that's fine. So after that, we are going to create an encoding, which is going to use the tokenizer. And right here, I'm going to basically use the same parameters that we used before. I want to add the special tokens, set a max length, which is going to be the max token length. I also want to not return the token type IDs. We are not using those. I want to apply the max length padding. We want to do a truncation. So this will basically make sure that each sequence is as much as 128 tokens long. I want to return the attention mask. And finally, we want to return the tensors as PyTorch tensors. So now that we have the encoding, we can return the item, which is going to be a dictionary, which contains the original or raw text of the comment. It's going to contain the input IDs, the attention mask, and the labels as tensors. Of course, the normal text is going to be returned just as a string. So I'm going to return the comment text. Then the input IDs. And I'm going to flatten those. So this will remove the excess dimension, which we observe when using the convert IDs to tokens. I'm going to do basically the same thing for the attention mask. And for the labels, I'm going to convert the integers that represent whether, or the integers that represent the flux of whether or not a comment belongs to a certain category, I'm going to convert those to a float tensor. This is basically required by the was function that we're going to use later on. And now that our dataset is complete, I'm going to execute the cell, and let's have a look at what we can do with it. I'm going to pass in the train df and the tokenizer that we have thus far. So I'm going to create an instance of that, and we are going to take an item from it. We are going to take the first item, and you can use a basic array-like access right here. So this will give us an item in this format, this dictionary that we created right here. So I'm going to check the keys of this item, of this dictionary, and you can see that those are exactly the same. So we can have a look at the comment text, for example. And you can see that this is the text in a raw format. You can check the labels, which should be a tensor, and there are, and note that this is a float tensor. Of course, we can check the input IDs, and I'm going to take the shape of those, sample item, and you can verify that this is 128 tokens long, so this is perfect for us. Now that we have our dataset, we can use a BERT model to do a sample prediction based on the single item that we have right here. And to do that, I am going to load a BERT model from pre-trained, and I'm going to use the BERT model name constant that we've created. And I'm going to pass in return dict, which is basically going to give us a dictionary, or in this case, rather a data class, which we are going to use in a second. And I'm going to run this. This will go ahead and download the BERT model itself. You can see that it's quite a large model actually. So after that, we can do a prediction. And I'm going to pass in sample item input IDs. And I'm going to unsqueeze those. So this will basically create this. Let me show you. So currently we have the input IDs, which is basically a flattened tensor, which contains the 128 IDs of the tokens that we have. And if I unsqueeze this, unsqueeze it at dimension 0, this will basically add another dimension right here. Why we need to do this? Well, basically the BERT model is expecting a batch which needs to be passed in, and we are going to pass in a batch of size 1. And I'm going to do the same thing for the attention mask. So we can get the prediction from here and check it. So this prediction is quite big. It's a quite large couple of tensors. So what we are going to do is to call, for example, the last hidden state, which is a property, because actually this returns a Python data class, and I can check the shape of this. And you can see that the last hidden state contains the number of hidden dimensions in the BERT model, which is this number right here, and then we have the number of tokens that we have. So for each token, basically we have the full hidden state of the BERT model, and we can basically go ahead and pull this output, or this is already done for us using the puller output. And as you can see, this basically flattens this and pulls the output. And if you wanna have a look at how this is done, you can go through the source code from the HuggingFace transformers library, and it's basically a simple pooling operation, not anything that particular or interesting. Some people do have better results with getting the last hidden states from here and applying some form of pooling that is different compared to the puller output right here. So you might want to check actually how the pooling is done and can you do better. Of course, that might result in better results, or it might just get worse. Who knows? Go ahead. The final step of our data preparation is going to be to create a data module that is provided, that extends from PyTorch Lightning data module. And this needs to be, of course, a class. And we are going to extend from the Lightning data module. Right here, we need a constructor that will accept the training and the testing set in a form of pandas data frames. We need the tokenizer, and here we're going to choose a batch size, and the maximum token length is going to pass in again. So this is a constructor with a lot of parameters, and here I'm going to call the super constructor. Then we need to assign the training data, test data, tokenizer, the batch size, and the max token length. Next, I'm going to create a method called setup, which is going to basically create a data set for each of the training and the test sets. And we're going to use the class that we've already defined, toxic comments dataset. And in here, I'm going to pass in the training data, the tokenizer, and the max token length. Next, I need to create the test dataset. I'm going to again pass in the tokenizer and the max token length right here. So now that we have those two methods, we are going to define data loaders for the train, validation, and test sets. And here I'm going to use the test set as a validation and test set. You can, of course, define another set which is going to be used strictly for validation or strictly for testing, however you choose. But here I'm going to take this shortcut, which of course might not be advisable to do in practice, but for the sake of this video, we're going to speed up things quite a bit. So I'm going to continue with the train data loader. And this method is actually required by the Lightning data module. So we are basically overriding this method. And here I'm going to return a data loader that uses the training dataset. I'm going to specify the batch size, which is going to be the batch size that we passed into our constructor. I want this to be shuffled just in case. And I want to pass in the number of workers, which is going to feed our model with for workers, so we won't have to wait for each individual example to be fed in. We are going to feed in a lot more examples than one at a time, or one batch at a time. All right, so next I'm going to do the validation data water. And this is pretty much the same thing. We are going to again use the same number of workers, but I'm going to use the test dataset, and I don't want this to be shuffled, and the batch size is going to be actually 1. So during validation and testing, I'm going to stay as close as possible to production environment, where more likely than not you will just make predictions on a single example. So we can reformat this. And then define the same thing for the test data water. So this is exactly the same. So after all this is complete, you can run this and create a data module right here. And I'm going to pass in the train data frame, the validation data frame, and the tokenizer. I'm going to keep the batch size at 8 and the number of tokens at 128. And I'm going to run the setup method. So this basically now has these two properties, and we are ready from here to define our model using PyTorch Lightning. And after that is complete, we are going to train the model into the next part.